Hello everybody, and welcome to the beginning of section 6.1 on page 128 of the workbook. In this section, we're going to introduce an idea called the inner product. And before we do, I would like to motivate that definition a little bit. So let's think back to one of the nicest vector spaces that we've talked about so far in this course, R2. Okay, one of the things that's nice about that vector space is that there's sort of a geometry that we can think about when we think about vectors in that space. For example, without picking a specific vector here, if I just pick kind of an arbitrary vector in R2 and call it U, it's possible to talk about concepts like orthogonality, let's say. In other words, we could think of other vectors that are perpendicular to that vector. Okay, 90 degrees between those. Another thing we can do in R2 is talk about projections, breaking a vector into components. So that U vector that we started with, we could think of its x component and its y component. That's something that you might do in a physics class. If you represented a velocity and you want to know what the velocity in the x and the y direction is. And these are nice things to be able to do in a vector space. So the question that we're asking at the beginning of section 6.1 is, could we impose that kind of a geometric structure on more abstract vector spaces? Okay, and the answer is, in some cases, yes, we can. And to do that, the first step is to introduce what's known as an inner product. Okay, so let's get started. We'll scroll up here. Okay, so let's read this definition together. So V is a vector space over F, and let's remind ourselves that F is just our field of scalars, which could represent the real or the complex numbers, depending on the situation. And an inner product on that vector space is a function that assigns to every pair of vectors, x, y, and v, a scalar denoted by bracket xy. And when you see this notation, bracket of xy, we're going to read that the inner product of x and y. That's what that notation represents. Okay, and this inner product of those two vectors x and y has to obey a set of rules, which we're going to list here. Okay, so as we read these together, keep in mind that x, y, and z are vectors, and c is a scalar from our field. Okay, so starting with rule A, tells us that if we take three vectors x, y, and z, and we take the inner product of x plus z with y, we'd like to be able to split that up into the inner product of x with y and the inner product of z with y. Okay, and then property B says, if we take the inner product of the scalar the scalar c times x with y, we can take that scalar and pull it out and take c times the inner product of x and y. And I'd like you to notice that those first two properties are kind of a linearity in the first coordinate of our inner product. Sort of reminds you of linearity from earlier in the course. Okay, so those are two properties that we'd like to be satisfied. Okay, and then the third property gets complex conjugation involved. So the complex conjugate of the inner product of x with y is, we want that to be equal to the inner product of y with x. Okay, and then finally, last property that we need to be satisfied is if you take the inner product of a vector with itself, then you actually get a positive real number as long as the vector is not equal to the zero vector that you started with. Okay, so an inner product is just a scalar, and I want to emphasize that again. When we take the inner product of two vectors, we're going to get a scalar. And to call it an inner product, we need these four properties, A, B, C, and D, to be satisfied. Okay, and if all of those things are true, then we'll call our vector space an inner product space with this inner product that we've defined. Okay, now to this point, this is all very abstract. It's a lot of new notation, properties, and you're probably asking yourself, why would we want to have these four properties and what do they really mean? Okay, well, we're going to do some examples in a minute, but I want to throw one thing out there before we do. Okay, so if you go back just for a minute to kind of the first sentence in the definition here. So we started with two vectors, x, y, and v, and the inner product wound up to be a scalar. Think back to multivariable calculus for a minute. Can you think of any vector products where you take the product of two vectors and what you get out is a scalar? Okay, if you think about it, the dot product. The dot product of two vectors from vector calculus behaves in kind of the same way. You start with two vectors, you take the dot product, and you get a scalar back. So if you like, you can think of this definition as kind of a generalization of the dot product. Okay, when we look at our first set of examples, that will be one of our examples.